Okay, so today we're going to start talking about tangent planes and linear approximations. So let's begin with what a tangent plane is. So if we have some surface in R3, so let's say this is our surface. What we can do is we can find the tangent line. So at any point P, so this will be the point P, which it will be A, B, and F of AB on the surface. And this over here is the surface F of X, Y, which will be equal to Z. And so we can find a line tangent to this point in the X direction as we let Y stay fixed. And the slope of this line at this point will be F partial with respect to X at the point AB. And we can find another line tangent to this point going in the Y direction where X is fixed. And that will have, this line will have the slope F partial with respect to Y of AB. Now, what we would like to do is we would like to find the plane that contains both of those lines. Or in other words, this plane will be tangent to the surface at the point P. And so we can ask, how can we find this plane? And we can draw two vectors that are contained in the plane. One of the vectors will be this vector over here. And the other vector will be this vector okay, and the other vector is going to be this vector over here, some vector going like that. And what we can say is that, let's say this vector over here is going to be in the form of, well, X is not changing along the vector. So X is 0. I mean, it's going only in the Z and the Y direction. It's not going in the X direction, so there is no X component. And we can say that if it goes 1 let's say, step in the y direction, it will be going f of y AB in the z direction. So this is the z component. This is the z component over here. This is the y component, and this is the x component of that vector. And similarly with the second vector, so that's this vector right over here, we can say that in the x direction, if it goes 1, then in the z direction, it's going to go f of x AB, right? As we take one step in the x direction, the amount that we move in the z direction is our derivative, f of x. And then it doesn't move in the y direction. So these are our two vectors that are contained in the tangent plane to the surface at the point P. And so now we can find the normal vector to our surface, the normal vector to our tangent plane, and it's going to be the cross product of I, j, k, the first vector, 0, 1, and fy at AB, and the second vector, 1, 0, and fx at AB. And so that will be in our ith component, we are going to have fx AB, just 1 times fx, and then minus 0. And then in our j component, we're going to have negative, and then we're going to have 0 times fx, which is 0 minus 1 times fy. So this negative disappears, and we get fy AB. And in our z component, we are just going to have 0 times 0 minus 1 times 1. So it's going to be negative 1. So our normal vector to a tangent plane, the normal vector is going to be f with respect to x at AB, the partial of f with respect to y at AB, and negative 1. Any questions so far? So now we can use the formula for planes, which says that we want the normal vector dotted with the vector x minus the point. So x minus the x component of the point in the plane, which is A, y minus B, and z minus C. And we want this whole thing to be equal to 0. So this will give us the partial of f with respect to x at AB, the partial of f with respect to y at AB, and negative 1 dotted with x minus A, y minus B, and z minus, well, C is f of AB. It's just what our function is at the point AB. And we want this to be equal to 0. So that gives us partial of f with respect to x, AB times x minus A, plus the partial of f with respect to y at AB times y minus B, minus z minus f of AB. Now we are used to seeing planes from the perspective of z. Of course, this is equal to 0. So we can just move this z to the other side, and we get z is equal to f of AB. So that's the point on the plane at P, plus partial of f with respect to A at AB, x minus A, plus partial of f with respect to y at AB, okay. Any questions so far? Yeah. Yeah, I mean, it every time it disconnects, I just can't write, so I need to refresh the. Plus the partial of f with respect to y at AB times y minus b. And this is the equation of a tangent plane. So if you're given your f and you're given your a and your b, you can now find the tangent plane to that surface. Yes.
Why did you change this to
So C is just the z point in the plane. C over here is just the z component. And this point in the plane is in the form AB and f of AB. So this is just C. It's just the z component of the point. Any other questions? Okay, so let's do an example. So if you have the function f of x, y is equal to x squared plus 2y squared minus y minus 4. Find and should at the point P is equal to 1, 2, and f of 1, 2. So the pieces of information that we need is what is f of 1, 2, right? That's this first part over here. What is f of AB? So what is f of 1, 2? Well, that's just going to be 1 plus 4 times 2, which is 8, minus 2 minus 4. And that's just going to be 8 minus 6, which is 2, so 3. That's the first piece of information that we need. The second piece of information that we need is what is f at x of 1, 2, right? That's this next part of information. What is f, partial of f with respect to x at the point where we want our tangent plane? So first, let's figure out what is f, partial of f with respect to x at x of xy. And that's going to be 2x. That's just that. And so then the partial of f with respect to x at the point 1, 2 is just going to be 2. Now the third piece of information that we need is the partial of f with respect to y at this point. So first, what is the partial of f? Partial of f with respect to y at xy? Well, that is going to be 4y minus 1. And so the partial of f with respect to y at the point 1, 2 is going to be 7. Any questions about this? Okay, so now we just put this formula together and we get that our tangent plane z is equal to f of 1, 2, which is 3, plus f partial of f with respect to x at 1, 2, which is 2, times x minus the point of the x component, which is 1, so minus 1 because of that one, plus 7 times y minus the y component of this point, so minus 2. And then we can simplify this, or we can leave it like that. And this is our tangent plane at the point 1, 2 for our function f. Any questions about this? So it ends up looking something like this. Our function is a paraboloid, right? We have x squared and y squared. And then we have some y, but you can always try to put it into the square. So it is a paraboloid. And at the point, so it looks something like this. And at the point 1, 2, that would be this point here, let's say. So this is the point 1, 2, f 1, 2. We have a tangent plane that looks something like that. And this is the equation of that tangent plane. Let's do another example. So if we have f of xy is equal to xy cubed plus 2x find the tangent plane at the point P is equal to 2, -2. So please take, let's say 5 minutes and do this problem. Okay, so again, we need 3 pieces of information. The first piece of information is what is f at 2, -2. So that's going to be 2 times -8 plus 8. Okay, never mind. And that is -12. And so then the next piece of information that we need is what is f, partial of f with respect to x. Sorry, yeah. Sorry, 1 second. Sorry, what was the question?
Yeah, I think just accidentally.
Okay, so then the partial of f with respect to x at 2, -2. So what is the partial of f with respect to x? This is going to be y cubed plus 2. And so the partial of f with respect to x at 2, -2 is going to be -8 plus 2, which is 6. Sorry, what? Oh. Yeah, -6. Okay. And then the partial of f with respect to y at 2, -2. So what's the partial of f with respect to y? This is going to be 3xy squared. And then the x is just constant, so it disappears. And so then the partial of f with respect to y at 2, -2 is going to be 3 times 2 times 4, which is 24. So once we get these pieces of information, we can say that our z is going to be our f at AB, which is -12 plus our f at x at 2, -2, which is -6. So -6 times x minus the x point, which is 2, plus the partial of f with respect to y at 2, -2, which is 24, times y minus or plus 2, minus the y component. And this is our plane. Any questions? Okay. So once we understand how to find tangent planes, there's another thing that we can do, which is to approximate our function at a point, or it's called linearizing the function at some point. So if we have some function, we can create a tangent plane at the point P. So this is the point P, which again is equal to A, B, f of AB. And we can create a tangent plane at this point. And then if we want to know what this value is, for example, on this function, what the value is near P, rather than looking at the function, we can instead look at the value for the tangent plane. So this is kind of similar to the linearization that we saw in Calc 1, or the differentials also that you see in Calc 1, which is if you have some function, you can linearize it near some point. So you can take the line at some point. And then if you want to find the value of this function, let's say here, instead of looking at that point, which might be complicated depending on how the function looks, you could look at the point at the line and approximate this point, the value of this point, by the value of this point. So we're going to try to do the same thing, just with 3D surfaces. So again, rather than try to figure out what the value of this point is on the function, we can try to figure out what the value is, let's say over here on the tangent plane, and it might be easier to do that. So we first call L of xy this tangent equation that we found, f of AB plus fx AB times x minus a plus partial of f with respect to y at AB times y minus b. And this is the linearized equation of f of xy. So we can think about it as the linear approximation to f at the point P, which is equal to A, B, and f of AB. So it's not for all points, but it is for points that are close to A and B. And we can then say that f at xy is approximately the linearized equation at or near AB. So there is some approximation between this linearized equation and our f, which means that f of xy is approximately f of a b plus the partial of f with respect to x at AB, x minus a, plus the partial of f with respect to y at AB, y minus b. Any questions? So let's do an example. So use linearization to approximate the value of 2.92 squared times the square root of 4.08. So questions like this are asked in Calc 1, but with only one type of value. For example, you can be asked to approximate the square root of, let's say, 3.01. at which point you take your f of x to be the square root of x, and you linearize it, and you use the linear equation to approximate the value at 3.01. So we will do something similar for this problem. So we can take our f of xy to be equal to x squared times the square root of y. And what this is asking us is, what is f of 2.92 comma 4.08? That's what this question is asking us. Any questions? So in order to solve this question, we just need to linearize our f of xy. So where should we linearize it? Well, we should linearize it at the points closest to these points, which seem natural and easy to deal with. So that would be the point for our x3 and for our y4. And again, we now need 3 pieces of information. What is f of 3 comma 4? So that's going to be 3 squared times 2, which is 18. Okay, the second piece of information is, what is f partial of f of at x at 3 comma 4? Well, so first, what is the partial of f with respect to x at x, y? So this is going to be 2x square root of y. So then what is the partial with respect to x at 3 comma 4? Well, this is going to be 6 times 2, which is 12. Now, the last piece of information that we need is the partial with respect to y at 3 comma 4. So what is the partial of f with respect to y at x comma y? Well, that's going to be x squared over 2 square root of y. And so then what is the partial of f with respect to y at 3, 4? Well, that's going to be 9 over 4. So now we can write our linear approximation. So our linear approximation, L of x comma y, is going to be 18 plus 12 times x minus 3 plus 9 over 4 times y minus 4. Any questions so far? So now if we wanted to find the points that we were looking for, which were 2.92 and 4.08, we can just plug it into our linear approximation. We can say a good approximation. So first, f at 2.92 comma 4.08 is approximately our linear approximation at 2.94 2.92 and 4.08. And now we can just plug that into our x onto our y. So we just take this and we plug it into our x. We take this and we plug it into our y. And we get 18 plus 12 times negative 0.08 plus 9/4 times 0.08. That's going to be 17.25. Now, if you plug this into a calculator, you would get that the actual value, so f at 2.92, 4.08 is exactly 17.22 or whatever, approximately. We see that these two approximations are fairly close. These, by the way, finding a linear approximation and approximating a point, it can definitely appear on the exam. So this type of question is definitely the type of thing that might appear on the exam at some point. Anyway, we see that these are pretty close approximations. If you wanted to know how far away the approximation was, you can just take 17. Why is that? Okay, let's say 17.25 minus 17.22 divided by 17.22 times 100%, just to get rid of the decimal. And this is 0.1%. So again, a pretty good approximation. Any questions? Yeah. Zoom out. Sure. Oh, it's the percentage, the change, the how much you're off percentage. 0.1%. Yeah. Any other questions? Okay, so I'm gonna go to a new whiteboard. So let's do a second example. So let's say we have r of x comma y is equal to the square root of x squared plus y squared over 2. And we want to show that this can be approximated by x plus y over 2 for x close to y. So how do we do this? Well, we need to find, so let's first imagine that the 2 points are the same. X is equal to y is equal to a, because we want them to be close. So we want to show when they're close to each other, we get that this is a good approximation. So then we need f of a comma a, which is going to be equal to the square root of a squared plus a squared over 2, which is going to be equal to a. And then we need the partial of r with respect to x. First, let's go with x, y. So this is going to be 1/2 times x squared plus y squared over 2 to the negative 1/2 times 2x, which is going to be so this and this can cancel. Sorry. Should what be 1? Oh, this whole expression? No, I mean not unless like x and y are cosine and sine or something. Oh, even if, well, they're not equal right now, we're going to plug in a, but this is going to be 1 x over the square root of 2 times x squared plus y squared. Sorry, for, yeah, x close to y, sorry. So the 1/2 comes down and it cancels with the 2 from the x squared. And then the negative just puts you down, and this 2 just comes up by rules of fraction. Inside, it should just be the 2 comes out and it goes here. So the, oh, sorry. Oh yeah, oh, another 2, I agree, sorry.
Sorry, is this x not equal to 2?
Yeah, let's just go with x and 1/2. Any other questions? Yeah.
That might be that's all right.
Behind, yeah.
Can you explain why we put it in terms of that? Why we do that at all?
Because we just want to find some number and say that they are equal. So we're going to just say that we want to find it at the point AA, where A is the same. So those are the points where these are going to be close, right? And if we approximate it near them, we'll get what we want, which is to show that we can approximate this equation by this over here, right? When x is close to y. Okay. Any other questions? Yeah.
Where's the 1/2 go?
So this 2 over here. Okay, let me just write this out. So this whole thing is going to be 1/2. Oh, shoot. Okay, this whole thing is going to be 1/2 2 over x squared plus y squared, right? And then you take the square root, and then we can put the 1/2 inside, but you get 4. So this will be the square root of 1 over, oh, and then there's an x, sorry, x. And then you get the square root of 1 over 2, because this 2 and this 2 cancel, the 4 when you put it inside, x squared plus y squared. And so this is x over the square root of x of, okay, let's go with 2 x squared plus y squared. Yeah. Any other questions? Okay, so same thing happens to the r with respect to y, because they're symmetric. So partial of r with respect to y at x comma y. Well, right, this looks the same. X between switching x and y doesn't really matter. So you get something that looks the same. It's going to be equal to y over the square root of 2 times x squared plus y squared. Now we can do our linear approximation. So L of x comma y is going to be f at AA, which we said was A. So A plus, and then if we plug in on our A, so what is R, partial of R with respect to X at AA? Well, that's going to be A over the square root of 2 times 2A, which is 4A squared, which is going to be 1/2 yeah, just 1/2, right? This is going to be A over 2A. And similarly, so this is going to be 1/2 times x minus A plus another 1/2, and then do the same thing with your ry of xy, and you will get that r partial of r with respect to y at AA is equal to 1/2 also. So that's just going to be 1/2 of y minus A. Okay, and then this A cancels with this half A and with this half A. So we get x plus y over 2. And so that gives us what we wanted. The approximation of this thing when x and y are close is going to be x plus y over 2. Any questions about this? Okay, then we're done for today.
Question from